Hello everyone, welcome to the channel. In this video I'm gonna show you the urban carbon monoxide monitoring and energy proxy visualization using Sentinel-5P and VIIRS imagery. Now let's get started. Rapid urbanization and increasing anthropogenic activity have led to a significant rise in urban air pollutants, particularly the carbon monoxide, which poses severe health and environmental risk. At the same time, the urban energy consumption pattern often linked to an economic activity that can be proxied through a nighttime light intensity captured by satellite-based radiometer. Monitoring these two parameters over time provides a valuable lens to evaluate the urban air quality and energy dynamics. This study aims to analyze the spatial temporal variation of the atmospheric carbon monoxide concentration and urban energy use proxy using Earth observation data from Sentinel-5P and VIIRS, that is visible infrared imaging radiometer suite. For a period of 2019 to 2024 within a selected urban region. The Sentinel-5P provides near real-time high-resolution measurement of trace gas, including carbon monoxide, whereas VIIRS captures nighttime radiance, which correlates well with electricity consumption and urbanization trend and economic development. Using Earth Engine, this work integrates and processes the massive satellite data for a monthly aggregation and visualization and analysis. A study area is defined through a polygon covering a targeted urban setting. The 5P data is used to monitor the monthly trends in carbon monoxide column number density, while VIIRS monthly composites are analyzed to assess the variation in average radiance. A reliable proxy for the electricity demand and urban activity. Through spatial overlay and time series visualization, this approach provides an insight into the relationship between the carbon monoxide emission and urban activity, helping to better understand the environmental implication of urban energy use. This type of analysis also supports an evidence-based urban planning and sustainable policy making and air quality management at local and regional scale. Now to calculate the urban carbon monoxide concentration as well as the energy proxy visualization using Sentinel-5P and VIIRS dataset, first we have to load our global administrative boundary into Earth Engine. To do that, first we're going to define a variable called boundary selection equals to Earth Engine.feature collection FAO 2015 level 1, and to add this layer we're going to define map.addLayer boundary selection with the default visualization parameter and output the layer name as global admin boundary. Now let us visualize this particular result here. Let me going to run this code. Now in the layer section you can able to see this is a global admin boundary layer. We're going to zoom out here. This is a global administrative boundary layer. From this boundary layer we're going to select our study area, that is my region of interest. For example, I'm going to select this I'm going to select this particular area called Shandong. I think it's a province. I'm going to select this particular Shandong using this particular tool here. That is draw a rectangle. I'm going to click here and I'm going to draw a polygon over this particular boundary area. Once you did that, next we're going to navigate this option. We're going to click this option called show generated code. And here we're going to copy this latitude and longitude of the study area. I'm going to copy this latitude and longitude of the study area using Ctrl C in my keyboard. And once you copied it, I'm going to close this. In the next step, I'm going to paste this latitude and longitude inside this particular variable called boundary coords. Now I'm going to paste it here using Ctrl V in my keyboard. Once you pasted your latitude and longitude inside this variable called boundary coords, next step we're going to create another variable called study area equals to earthengine.geometry.polygon boundary coords. This particular refers to this variable here called boundary coords. Earthengine.geometry.polygon, it's going to convert this latitude and longitude into a polygon. For that we are mentioning earthengine.geometry.polygon. It's going to convert this latitude and longitude into a polygon. And the next step we're going to add this layer. To do that we're going to define map.addLayer study area with the default visualization parameter and output the layer name as study area. Now let me turn this off here. Now in the layer section I'm going to navigate to the layer section. I'm going to turn off the global admin boundary layer. I'm going to turn this on the study area. So you can able to see we have added this study area. And the next step to select this particular global admin boundary. So we're going to select this particular boundary polygon from the global administrative boundary layer. So for that we apply this particular study area. So using this study area, so we're going to clip out this particular boundary out from the global administrative boundary layer. So to do that, in the next step, again we're going to load this administrative boundary layer, that is variable admin boundary equals to earth engine dot feature collection, referring to our global administrative boundary layer. And the next step, to clip out this particular boundary out of this global administrative boundary polygon. So I'm going to clip out this particular admin boundary polygon, that is Shandong of Shandong province in China. So to clip out, we're going to mention another variable called region mask equals to admin boundary dot filter bound based on our study area. And dot we're going to use this map function in order to simplify this polygon. So for that I'm going to mention dot map function f, and we're going to return f dot simplify 500. So basically it's going to simplify the polygon here. And the next step, we're going to center this particular layer. So to do that, we're going to define map.center object region mask. And the last step, to add this layer, we're going to define map.add layer region mask with the default visualization parameter. And we're going to output the layer name as simplified AOI, that is area of interest. So now we're going to visualize this layer called simplified AOI, that is our area of interest. And I'm going to turn off all of the layers, and I'm going to turn on simplified AOI, that is area of interest. So now you can able to visualize it. We have managed to crop out of clip out this particular polygon out of the global administrative boundary polygon. So this is going to be our study area polygon. And the next step, we have to fix the time series for our analysis, the time period of start of our time analysis and the end of our analysis. So to fix that, we have to use another set of variables. For example, we're going to create a variable called start year equals to 2019. And next we're going to mention the end period of our analysis, that is variable end year is equals to 2024. So now we have managed to fix the start and end year, that is 2019 and 2024. The next step, we're going to load our Sentinel-5P CO dataset and filter it by the time and region. So we're going to filter it based on the time period and the region of interest. So to load our Sentinel-5P carbon monoxide dataset, we're going to define a variable called CO dataset equals to earth engine dot image collection Copernicus S5P NRTI L3 CO. So now let me show you this particular dataset here. So this is Sentinel-5P NRT CO, that is carbon monoxide, near real-time carbon monoxide. So the dataset availability starts from 2018 to 2025, and the dataset provider is European Union ESA Copernicus. And using this code, you can access this particular data, that is a Sentinel-5P NRT carbon monoxide concentration dataset. And you can go through the description about this particular dataset. So this particular dataset provides the near real-time high-resolution imagery of carbon monoxide concentration. So the carbon monoxide is an important atomic trace graph for understanding the tropospheric chemistry. So in certain urban areas, it is the major atmospheric pollutants. So the main source of carbon monoxide is the combustion of fossil fuels, biomass burning, and atmospheric oxidation of methane and other hydrocarbons. Whereas the fossil fuel combustion is the main source of carbon at northern mid latitude, and the oxidation of isoprene and biomass burning plays an important role in the tropics. So you can go through the details about this particular dataset. So now let's navigate to the band section here. So the resolution of this particular imagery is around 1000 meters. So you can able to see from this pixel size here, this is the resolution of this particular dataset. So now we are interested in this particular dataset called carbon monoxide CO column number density, and the unit in moles per meter square, and the minimum and maximum value, and the description is a vertically integrated carbon monoxide column density. So these are the following other bands that is available in this dataset, starting with the H2O column number density, followed by the cloud height, and sensor altitude, and sensor azimuth angle. And you can see the different other bands that is available here. So you can go through the description of each of this band here. So now let me get back to Earth Engine. So the next step, once we created the variable and we use this code to access the carbon monoxide dataset. Next, we're gonna select this particular band. That is this is the band of our interest. That is carbon monoxide column number density. So we're gonna mention dot select carbon monoxide column number density, the band here. Let me show you that. So I'm gonna mention this particular band here. So I'm gonna select this particular band, that is carbon monoxide column number density. So the next step, we're gonna filter it based on our time period of analysis, that is start year and the end year. So to fix our time period of analysis, we're gonna mention dot filter date start year, so which represents this particular year, that is 2019, and the end year, which is end year, which represented in 2024. And last, we're gonna filter it based on our study region. So we're gonna mention dot filter bounds and region mask based on our study area. And the next step, we're going to generate the monthly aggregation of these dataset here. So we're going to generate a list of years from 2019 to 2023. So for that, we're going to mention a variable called years equals to earth engine dot list dot sequence parse int, and we're going to mention the start year. And last we're going to mention as parse int end year. So that is 2024 and -1. So which gonna indicates that we have analysis periods only from 2019 to 2023. Similarly, in the next step, we're gonna create another variable called months, which is equals to earth engine dot list dot sequence. So one which indicates January to December, that is from January to December. So in the next step, we're gonna create another variable called monthly carbon monoxide. So this particular variable we created in order to create a new image collection to hold the monthly average carbon monoxide dataset. So for that, we're going to mention the variable called monthly carbon monoxide equals to earth engine dot image collection years dot map function y, and the year so represents this particular variable which holds the yearly carbon monoxide dataset. And the next step, we're going to mention as return months dot map function m represents the month here. So month which represents this particular variable where it holds the monthly carbon monoxide, that is the carbon monoxide concentration. So by basically this iterates over the year y and each month m to create a monthly summaries of carbon monoxide concentration. And the next step, we're going to create another variable called month image equals to core dataset. So this particular step essentially isolates all image from the specific month and year. So we're going to apply filter function dot filter earth engine dot filter dot calendar range start year and end year, and the units it is in the year. And similarly, we're going to apply the similar step dot filter function earth engine dot filter dot calendar range, the start of the month and the end of the month and the unit in the month. And last, we're going to apply this particular function called dot mean function. So it computes the monthly average carbon monoxide concentration in moles per meter square for that month. And in the next step, we're going to create another variable called month start. So essentially, we are creating this particular variable called month start in order to create a date for the first day of that month. So for that, we're going to mention a variable month start equals to earth engine dot date dot from year, month and day. So that is year, month and day. So it's going to create a day for the first day of that month. So basically, it's going to create a date for the first day of the month. And next step, we're going to return the month image, and we're going to mention dot set system time start and month start in millisecond format. There is a millisecond function. So the set this as basically it sets this as a system time start property, so that the charts and the time series are chronologically accurate. So for that, we are mentioning this. And the last, we're going to apply the dot flatten function. So flatten function basically merges all year months image list into one flat image collection. And last, to add this layer, we're going to define map.add layer monthly carbon monoxide referring to this particular variable. And dot, we are applying a mean function in order to acquire a mean image, a mean carbon monoxide concentration image for the entire time period from 2019 to 2023. For that, we're going to mention dot mean function. And next, we're going to apply a dot clip function based on our study region, that is region mask. So this is our region mask. and we are setting the minimum value and the maximum value, and color palette starting with white, orange and red. So white, which indicates the lowest carbon monoxide concentration, and the orange, which indicates the moderate level of carbon monoxide concentration, and red, which indicates the highest level of carbon monoxide concentration. And we're going to output the layer name as mean carbon monoxide moles per meter square, which is the unit. So now let us take a look at the layer section here. So we're going to navigate to the layer section, and in that we're going to click this option called mean carbon monoxide. So from the study area, I can able to see the color patterns here. So the color palettes we are given for this particular, starting with the white, orange and red. So I can able to see the most of the study area is covered by this particular color in orange color, which indicates the moderate level of carbon monoxide concentration. So in the layer section, I'm going to navigate the layer. I'm going to click this option, and let me stretch this particular image. So in the custom section, I'm going to navigate and select this option called the stretch 90%. And once you applied your stretch type, that is 90%. So now we can click apply here. So we can able to see the value ranges from 0.045 moles per meter square to 0.060 of molecules per meter square. This is a concentration of carbon monoxide. So we're going to click apply. And now here you can clearly able to visualize this particular imagery. So you can able to see here. So let me adjust the transparency of this particular imagery. So we're gonna adjust the transparency using this particular option. So you can able to see here the highest concentration of this particular study area, that is Shandong. So which is observed, the carbon monoxide concentration is observed in this central part of the study area. So the red color, which indicates the highest level of carbon monoxide concentration, and towards the northern eastern part of the study area. So this particular area has a red color, which indicates the higher level of carbon monoxide concentration for the study area, and the white patches, which indicates the lowest level of carbon monoxide here. So towards the eastern part, you can able to see the carbon monoxide concentration is almost very less here, or it's almost very less compared, you can able to see. And also in the central part, some portion of the study area has a lower level of carbon monoxide, but few parts have a higher level of carbon monoxide concentration here. So we can zoom into this particular study area, and I'm going to turn to a satellite mode, and I'm going to turn off this simplified AOI, and you can able to visualize this. These are the industrialized area. So you can able to see this industrialized or this particular or urbanized area. So these urbanized areas have a higher level of carbon monoxide concentration, especially this particular areas. So you can able to see this particular urbanized area has a high level of carbon monoxide concentration. So it is possibly maybe due to the vehicle emissions, which might be the cause of this particular the high level of carbon monoxide concentration in these areas, or some industrial activities might cause this. So let me zoom out here, and let me navigate this. I'm gonna adjust the transparency. So I'm gonna close this. So the next step, so we're gonna create a time series chart for carbon monoxide concentration for this study region. So for that, we're gonna mention the print ui.chart.image.series and image collection. So monthly carbon monoxide, referring to this particular variable we have created earlier here. And the next step, the region is study area, that is our region of interest. And the reducer, it is earth engine.reducer. We are applying this statistical function in order to acquire a mean carbon monoxide concentration. So for that, we're going to mention earth engine.reducer.mean function, and the scale I'm going to mention as 7000. So the resolution of this particular imagery is around 1000 meters. So in order to increase the speed of our analysis, I've mentioned this resolution for around 7000 for the time series analysis. So for that, I'm going to mention the scale as 7000, and the X property is system time start. And to set additional options to this time series chart, we're going to mention as dot set options, title monthly carbon monoxide concentration over the area of interest, that is moles per meter square, and H axis, the title I'm going to mention this date, and the V axis, the title is carbon monoxide concentration, and the line width is 2, and the point size is 4, and color, we're gonna given this set of color for our time series chart. So now let us take a look at this time series chart for the carbon monoxide concentration. So the monthly carbon monoxide concentration over the area of interest in moles per meter square. So this particular axis represents the carbon monoxide concentration, and this particular axis indicates the date. And you can able to see the concentration of carbon monoxide ranges from 0.02 moles per meter square to 0.08 molecules per meter square, and this particular color which indicates the concentration of carbon monoxide. So based on our time series chart from time series analysis from 2019 to 2023, so you can able to see. So now we're going to click this option here. So now you can able to see the trend in the carbon monoxide concentration for this specific study region, Shandong here. So the carbon monoxide concentration during 2019 was pretty higher, as you can able to compare with the 2023 year. The concentration of carbon monoxide has been significantly reduced here. So you can able to see the concentration trend here. This particular graph, the concentration of carbon monoxide has decreased significantly from 2019 to 2023. So one of the possible reason might be in this situation is might be due to the use of electrical vehicles and hybrid vehicles, and reducing the traditional fossil fuel based vehicles. So we can able to see the concentration has been decreased in the study region, and we can also confirm this particular result using our VIIRS dataset here. Based on the energy consumption pattern, we can estimate the possible reason for this reduction in the carbon monoxide concentration for this specific study region. So in our VIIRS dataset, so let me get back to Earth Engine. So now last to export this particular carbon monoxide image to our drive. So we're going to mention export.image.drive, and image is monthly carbon monoxide dot mean function, and we're going to clip it based on our study region, that is our region mask. And the description I'm going to mention as monthly average carbon monoxide, and the resolution is around 1000. So the resolution of this particular image is 1000 meters, and the region is the region mask dot geometry, and the folder we're going to mention is urban air quality, the max pixel value. So the next step, we're going to load up a VIIRS Nighttime Light dataset here. So to load this particular dataset, we're going to mention a variable called VIIRS Night equals to Earth and dot image collection NOVA VIIRS DNB monthly V1 VCMCAFG. So using this code, you can access the VIIRS Nighttime Light dataset here. And in that, we're going to select this specific band called average radiance. So let me navigate to this particular dataset here. So this particular data is the VIIRS Nighttime day and night band composite version. So the dataset availability is from 2012 to 2025, and the dataset provider is Earth observation groups. And you can go through the information about this particular dataset here. So monthly average radiance composite image using the nighttime data from the visible infrared imaging radiometer suite day and night band. So you can go through the information about this particular band. So now we're going to navigate to the band section here. So the resolution of this particular data is around 500 meters of resolution. So you can able to see from this image. And the band name is average radiance, and the unit is in nanos watts. So radiance per centimeter square, and the minimum maximum value, and the description is an average DNB radiance value. So now let me get back to Earth Engine. So to access this data, we mentioned as Earth Engine image collection, Earth Engine dot image collection NOVA, and monthly V1 VCM CFG, and we're going to select the particular band, that is average radiance. As I mentioned earlier, we're going to select this particular band called average radiance using dot select average radiance. So I can able to see the units. And next is selects only the average radiance band, which quantifies the brightness of the artificial light at night. So next we're going to filter based on the timeline, that is the time period for analysis, that is dot filter date, start date and end date, that is start year and end year, that is 2019 to 2023. And the next we're going to filter it based on the calendar range. So for that, we're going to mention dot filter Earth Engine dot filter dot calendar range, and particularly we are excluding this particular month, that is month 6 and month 7. that is June and July, we are excluding this particular month using dot not function. So the not function inverts the filter out. So it excludes the image from June and July. So in order to remove the outliers due to the seasonal cloud contamination and noise from the environmental factors or the holidays time during this period. And the next to add this layer. So particularly we are excluding this set of month. For example, in case if your particular year any country which has celebrates light festivals, in order to avoid that particular timeline, so we are removing this set of month. So you can mention the month according to your choice. For example, in India, so during the light festivals, we can avoid the time during the December time, the November and December. So during the time the light festivals can interrupt our interpretation. So to avoid that, we are excluding this particular set of month for the study area. So likewise, you can choose your month according to your study area. So next, to add this layer, we're going to define map.add layer VIIRS night dot main function. So we're going to in order to add this layer and to acquire a single VIIRS image of some entire timeline from 2019 to 2024. So for that, to get a single image, we're going to mention dot main function to get a mean VIIRS dataset, and we're going to clip it based on our study region, that is region mask, that is our this particular study region. And we're going to set the minimum and maximum values and the color palette starting from black to white. So white, which indicates the highest brightness of artificial lights, and the black color which indicates the absence of artificial lights. And last, we're going to output the layer name as mean nighttime light. And let us visualize this image here. So we're going to navigate to the layer section, and I'm going to turn on this layer called mean nighttime lights, and let us visualize the result here. So now here you can able to visualize this is nighttime mean nighttime light dataset here. So now here in this, from this image, you can able to visualize all the white areas which indicates the artificial light areas, and all the black areas which indicates the absence of artificial lights. So we can able to see here all the urbanized area have this kind of artificial lights which is indicated in the white color. So you can able to see that. So now let's compare the carbon monoxide concentration here. So you can able to see these two dots has a higher level of carbon monoxide concentration compared to the other urban areas here. Let me adjust the transparency here. So you can able to see that the white spot in these two areas has a high level of carbon monoxide concentration, and also this small white spot has a high level of carbon monoxide concentration. So this particular areas with the low urban areas has a higher level of carbon monoxide concentration. So you can able to see from this image. So probably it might be in an industrial area. So that's why this even as presence of small urbanized area has a higher level of this carbon monoxide concentration. So you can able to see. So let me turn on this transparency to back to the original. So now we can able to see this image. So the next step, let us visualize this particular that is VIIRS dataset as a time series chart. So to create a time series chart for the nighttime light as a proxy for electricity uses, so we're gonna mention print ui.chart.image.series, and image collection we're gonna mention is VIIRS night, and region we're gonna mention the study area, and reducer is earth-engine.reducer.mean function. So we are applying a statistical function. So for that we have mentioned the earth-engine.reducer.mean function. And the next step, we're going to mention the spatial resolution to be around 500. And next property is system time start. And additionally, we're going to set this option dot set options. The title to be monthly nighttime light intensity. The proxy for electricity use. And the h-axis, we're going to mention the date. And v-axis, we're going to mention the average radiance. And the line width is 2 and the point size is 4. And color for this time chart is given this set of color. And now let us take a look at the time series chart of this particular one. There is monthly time nighttime light intensity, proxy for electricity consumption. So this particular axis represents the average radiance. That is the artificial brightness level. And this particular axis indicates the date. So now let us view this graph here. So you can able to see here during this particular year, that is during 2019, the consumption of electricity, that is the artificial brightness, that is the artificial light is pretty low during this set of year, and as a trend increases towards the 2023, you can able to see the highest level of the artificial light energies is used here. So which indicates it can be used as a proxy for electricity use. For example, During 2019, the consumption electricity, the artificial light was emission was pretty lower compared to 2023, which indicates that electricity consumption has might be increased in this study area. So the one of the graph which indicates the carbon monoxide concentration has been reduced during from 2019 to 2023. You can able see from this graph. And the second graph which indicates that the consumption of electricity might increase from 2019 to 2023. So possibly might be which might be use of the hybrid vehicles and EV vehicles in this study area. That is Shandong province in China. So which might resulted in the lower emissions of carbon monoxide concentration due to the shift in the electric vehicles in the study area. So you can compare this both the graph here. So one of the graph is showing the decreasing trend, and the second graph is showing the increasing trend in the study area. And you can able to see from this compare from the both the graph here. And after that, to export the once we have exported the carbon monoxide concentration, so we're gonna navigate to this task section to export the carbon monoxide concentration image to export this to a Google Drive. So we have this unsubmitted task called monthly average carbon monoxide. So we're gonna click this option called run to initiate the image export. So this is monthly average carbon monoxide, and the coordinate reference system is EPSG3857, and the resolution is 1000. We're going to export to a drive, and the file format is in GeoTIFF. And now to export to a Google Drive, so we're going to click this option called run. So the next step, we're going to take a look at the application part of this analysis and the interpretation of this result. So now let us take a look at the interpretation of the graph. So carbon monoxide concentration versus the nighttime light intensity. So the first graph which indicates the monthly carbon monoxide concentration over the study area in moles per meter square, and this particular second graph which indicates the monthly the nighttime light intensity. So the artificial brightness level, so which is indicated in this graph here. So based on the monthly carbon monoxide concentration over the study region from 2019 to 2023, so the carbon monoxide concentration generally ranges from 0.04 to 0.06 moles per meter square. A gradual decline in the carbon monoxide level from 2019 to 2021. The small seasonal peak around early 2020 and early 2022. A slight rebound in carbon monoxide towards the late 2023. So the possible interpretation, the drop in 2020 might reflect the reduced industrial activities and transportation during the COVID-19 lockdown, and the seasonal variability could relate to temperature and the vehicular emissions and crop residues burning. And the second one is the monthly nighttime light intensity, the average radiance, and the unit is in nanowatts centimeter square per radiance. So the trend is begin from around the value ranges from 1.8 to 2.0 average radiance in 2019, shows an increasing trend over time. The peak value exceeds 2.8 average radiance by late 2023. So more variability is visible, and especially in post 2021. The possible interpretation is increased nighttime radiance indicate the urban expansion, rising electricity use, or economic recovery post COVID. So the temporary dip in mid 2021 and mid 2022 may respond to the seasonal reduction and energy restriction or cloud contamination. And the comparative insight is the inverse trend. While the carbon monoxide concentration generally decreased and the nighttime light intensity increased, suggesting the urban electrification and lighting expanded, but the possible with the cleaner energy sources or improved emission controls. And the post 2021, both the dataset exhibits a slight increase and implying resumptions of economic activity and possible increase in energy demand. So this is a table showing the carbon monoxide concentration and light intensity in the trend from 2019 to 2023, the gradual decline and then stabilization, and the light intensity steady increase. And implication, the reduced emissions or improved air quality, and in case of light intensity, urban growth and increased electricity consumption. Another possible reason might be discussed earlier due to the conversion from the fossil-based fuel to EV electric-based vehicles might have decreased the carbon monoxide concentration, and which increased the electricity consumptions. One of the possible reason from our analysis. Now let's take a look at the application part of this analysis. So the application of this study is urban air quality monitoring. Monitoring the code enables us to continuous tracking of carbon monoxide concentration over the cities, industrial zones, over the cities or industrial zones. So it helps to identify the pollution hotspot, seasonal trends, and long-term changes in carbon monoxide linked to transport, heating, and industrial emissions, and environmental policy support. Monthly carbon monoxide trend can inform the urban emissions inventories and appliances with air quality standards. The outputs can be used to design the mitigation measures such as low emission zones or traffic restrictions. And the third application is the public health risk assessment, linking a high carbon monoxide concentration to a populated areas, supports a health risk assessment for exposures, and health departments can prioritize an intervention during the months with an above average pollutions. And the fourth application is energy consumption analysis. So VIIRS, the nighttime light, serves as a proxy for electricity consumption and economic activity, comparing the carbon monoxide emission with the nighttime radiance helps to explore the relationship between the energy use and air pollution. And the fifth application is in urban growth monitoring. So the temporal series of the nighttime light reveals the urban expansion and densification and economic development patterns, and planners can correlate the radiance increase with the infrastructure developments. And the sixth application is the climate and sustainability research. The results contributes to understanding the urban contributions to the climate relevant gases in the heat emissions, supports the sustainability assessment and CDG monitoring, particularly goals related to the health, energy, and sustainable cities. And last application is the disaster and emergency preparedness. So during the events like wildfire, industrial accidents, or power outage, the system can detect the sudden changes in carbon monoxide and the nighttime radiance. And these are the following applications for this analysis. Let me get back to Earth Engine. So in this video, I've shown you urban carbon monoxide monitoring and energy proxy visualization using Sentinel-5P and VIIRS imagery. So the code link will be given in the description. So thanks for watching, and make sure that you subscribe to our channel and give us a like.